Good afternoon. Tuesday, May 2nd, 2023, 15:30. Hello, gentle listeners. Welcome to another hour or so of reading about Albert Einstein from Einstein. His book, Out of My Later Years, which kind of represents what I was happy to discover as a sort of statement of position about his opinions of his desiderata and requirements of a future theory, and specifically what he calls total field theory. That these days, with particle physics and quantum mechanics and general relativity and astronomy and high-powered experimental physics and mechanics and everybody together, all in the same boat, it's pretty well understood that space-time is flat, and the theory is a field theory, and the theory is a gauge theory, and that the total field is isotropic, that there does not appear to be anywhere in the universe where the laws differ, so somehow it must all add up. There is a lot of phenomena that's rather extensive. And these days, the Sky Survey had a couple really pretty amazing things going for it. And that was after the Hubble Space Telescope, which was awesome. And I've never really just spent time poring over images from outer space, because many of them are basically can't really be reflected in true tone continuous images of a sort, because it's gathered in the spectral data. And so they're pretty much almost all usually artists' renderings thereof, or in the optical perspective, compared to radio astronomy and visible astronomy and microwave and then thermal astronomy vis-a-vis optical astronomy. And then there was 2MASS. And it was discovered 20 or more years ago that what we thought was the remnants of the Big Bang is really just our place in the local supercluster called Laniakea. It's a Hawaiian word, and it means garden of the sky or something like that. That the Lania, I'm not quite sure how it's pronounced, is a garden. And so the Milky Way, along with all the galaxies all around us that have been in the visible universe up to that point, is as far as they're expanding, because it had always been found that just like there had been an origin and a Big Bang theory, that according to classical mechanics, everything was just kind of falling apart, falling away from each other, increasing, expanding, inflating, that the redshift was pronounced and usual, and this is the Doppler redshift blue shift, that something that's going away has a redshift and something that's going closer has a blue shift, according to what they're determined from what are called standard candles and various types. After it was possible to determine from hydrogen spectroscopy, the hydrogen line, then it was figured out that would be pretty universal, because it gets through dust and it gets through the interstellar media, in terms of why, if you're interested in the cosmology and the Sky Survey, some things to know about are standard candles, which are stars of particular types of presumed origin that have light of a given well understood range can be detected. And these standard candles, by their luminosity that's detected here, are used to determine distance, and they're used to measure distance, because there's no other meter or metric for distance that far away. There's not parallax, there's not a ground observer on the other side or what. So there's standard candles, and then there's the hydrogen spectroscopy, and I kind of learned this from a guy named, what's his name? Sullivan's book, Are We Not Alone, or something like that. And this guy named Sullivan, he wrote this great popular press book, and it's about like, well, if there's infinitely many galaxies, and each one of those has infinitely many stars, and any number of those, according to the Drake equation, has planets that develop life and intelligent life and ... Are we not alone? He describes some of the early searches for organization that would be of above the organization that just results from dynamics, the organization which results from a sort of opposite of entropy, or entropy into the organization, whatever is the gradient, or isotropic or anisotropic, represents whatever that flow would be. So there's standard candles and hydrogen spectroscopy. And so the redshift measurements came up about that. Then when 2MASS came up, it came out kind of quietly. It was like 2MASS has reevaluated what is redshift and what is blue shift. It's no longer 99% redshift. Now it's 51% redshift. That we basically live otherwise in that objects are moving pretty much as if they're at random motion. So what this means is that then it's kind of established that there's not anisotropy of the space and time. And a lot of the stuff that went into fitting the model for Big Bang theory, called inflationary theory, what happened after it was just a very hot, dense gas of very primordial elements, this narrative of a deconstructive account that explains all the data. It fits all the data. So these days, that's left up and over about that gravity there's a couple competing theories. One's called MOND, modified Newtonian dynamics, and it kind of explains how galaxies appear to both cohere together, like the kind of in the Einstein's way. Einstein's way is the same. And for massy bodies, and with an inverse square. And then there's this just inverse, galaxies are so far apart, then they're rotational in their own frames that they don't appear to have the same behavior over the space. But if with the modified Newtonian dynamics, most of what's left over is to replace luminous matter, or that which would be detectable, because besides its gravitic effects, that it would be observable otherwise. That it's just not like filaments of black holes everywhere, or dark matter, which doesn't really emit a solution like a gravitational singularity or a black hole emits a solution just because it's the result of a particularly dense state of matter, and those are kind of observed, and they advise also that there are metaphors or models of them as any kind of singularity. That the idea of this dark matter and dark energy in the universe is basically what's left over, because it has to explain these things when otherwise the stuff has been coming online, that it's just been creeping more and more, and that this non-existent, non-scientific lack of explanation is put into place because that's what's left that fits the model and fits the rest of the data and fits the theory. So that MOND has come a long way, and then there's for the Earth, it's around the Earth, it's called parameterized post-Newtonian, and it adds up, including some relativistic effects and frame dragging and these things, why the various satellites in Earth are able to remain synchronized, and these kinds of things with regards to dead reckoning and their visual and radio location, and also their clocks they carry on board, and with regards to their clocks advising the changes in the space-time configuration around them, vis-a-vis their acceleration and the predictions of their behavior according to relativity. So anyways, that was pretty quiet. And then what happened is James Webb Space Telescope was launched, and this was a tremendous initiative, and it's launched all the way away from Earth out to basically a point behind the moon, or in front of the moon. There's the L1 or L2, or the LaGrange points in cosmology and orbits. So in these orbits, then there are a couple places that are stable, kind of like geosynchronous orbit is a sufficient height that its orbit, according to its velocity of the orbit, will always maintain the location of an object at the same point over the Earth, geosynchronous orbit. And so the idea of these Lagrange points is they're just naturally the dips or wells in the gravitational field, where they don't need constant effort to stay in the same relative location to the Earth and the moon. It just kind of follows it around. And so there's a couple other experiments out there at the Lagrange point. And so James Webb Space Telescope has blown wide open all these things that are like, this does no longer fit. This no longer fits with the Big Bang model, Big Bang theory, which is a separate theory altogether than relativity theories, and that it's really an exciting time. Now, sometimes it helps to be familiar with all sorts of cultural references. And so some people want to live in an exciting time because they figure it's an opportunity to improve oneself, or that things could change for the better. But for other people, it's bad because it means that we're just happy how the way things are, and anything else would be worse. And so it's a Chinese curse. May you live in exciting times. Whereas for other people, it's a wish, and so these kinds of proverbs and stuff are kind of like the Japanese saying, if you believe everything you read, maybe you shouldn't read, maybe you shouldn't believe, but you should have a critical outlook to sayings like that one that just was. These are kind of reflect the inspirational bit of, may you always live in a milieu where things have sensibility and sensicality, even when that they don't, because that's what reason is for, and it's a great thing. So anyways, Lagrange, besides the Lagrangians here, Lagrange is famous for a lot of time-dependent systems. So anything in dynamical modeling is parameterized by one variable called t for time. And it represents the clock time, represents calendar time, represents the passage of time, it represents the epoch, it represents the state of things in their evolution. Time is a universal parameter for the forward fall into the future. And in that sense, then there's uncertainty and chance, which basically advise all such matters as what established for the laws of some of the various laws of large numbers, the stochastic, or what will be expected predicted behavior over time, or the probabilistic. That which is defined or governed by particular distributions, which accordingly define an event space of samples, the sample space, also called the support space of all the samples, and that within this are events that occur, and that for any particular sampling with replacement or sampling without replacement, for the sampling, observer, and measurement effects, sampling something over time, sampling something and establishing a quantification of it, quantization of it. The Lagrange is famous for that. And so today when we talk about all this field theory and about how it was a very big deal that the Laplacian adds up for everything everywhere, why it's so kind of classically Laplacian with the establishment metric, and then the Lorentz transformations basically observe the Laplacian. Well, and that's not too different a time when Lagrange came around. So you got Laplace, Lagrange, and say Liouville or somebody like that for Sturm Liouville and solutions to various forms of ordinary equations and differential. So anything these days that's defined and parameterized by time is the Lagrangian. And so for a long time, it was just like everything follows out after the Laplacian, because then you can get Hamiltonians and these systems that have transitions and propagation according to Bra and Ket and these kinds of things, all the way down to scattering theory and da. These days it's the Lagrangian. It's basically everything's parameterized by time. And these are the systems equations that result what would be Einstein's desideratos was mentioned last time in reading about the field and the fields of electromagnetism, particularly Faraday's and Maxwell's classical fields, the electric field, behavior of objects in the electrical field, and the behavior of optical light, and the behavior of radio waves in the vacuum and in the electrical field, respectively. That the Lagrangian is what he'd expect his differential equations to be in. So, chapter 13, section 4, the theory of relativity. And this is in his chapter, Physics and Reality. There is no inductive method which could lead to the fundamental concepts of physics. So induction is forward inference, inductive inference. An inductive method is from what's so defined, what so follows. So Einstein is saying that the fundamental concepts are not inductive. Here it's been being discussed as a deconstructive account because we already have classical concepts and it's got to add back up to them. We need a deconstructive, reconstructive account. But besides inductive inference, then the other side of that is deductive inference. That basically a process of elimination compared to that which is constructivist. And so this gets into the intuitionist and the constructivist in the earlier talks where we talked about Einstein's description of theory, and that a theory of everything that's abstract is the philosophers, because the only way we can really access it is via an object sense that is a shared learned object of reason that still people can communicate and hold in their minds via the reasoning faculties and the reasoning facilities. And then we can so model it by anything what so models it, and call that physics and call that probability theory and ... Now, but what Einstein has just said, that there is no inductive method which could lead to the fundamental concepts of physics. Failure to understand this fact constituted the basic philosophical error of so many investigators of the 19th century. It was probably the reason why the molecular theory and Maxwell's theory were able to establish themselves only at a relatively late date. Logical thinking is necessarily deductive. It is based upon hypothetical concepts and axioms. How can we expect to choose the latter in such a manner as to justify us in expecting success as a consequence? This is being framed here in these complementary duals. It's a dialectic. Dually self-inferent consistency. Axiomless natural deduction. A theory. A number theory. A geometry. The logic. Logical thinking. How can we hope to choose the latter in such a manner as to justify us in expecting success as a consequence? The most satisfactory situation is evidently to be found in cases where the new fundamental hypotheses are suggested by the world of experience itself. One might gather. Evidently, clearly, obviously, lacking otherwise plain grounds for reason for its own sake of a sort. He's explained that anything that's in this physical theory, it really has to be empirically so, because otherwise it doesn't afford the models necessary to deal with it. But otherwise, this is kind of disagreeable because it's evidently not so when what he just said contradicts itself a little bit. The hypothesis of the non-existence of perpetual motion as a basis for thermodynamics affords such an example of a fundamental hypothesis suggested by experience. The same thing holds for the principle of inertia of Galileo. This is the principle of least action. That nothing is free, and that it works with their conservation laws and symmetries, that otherwise there would be no determinism, that causality is so attached that it's very close to a principle of least action to have the second law of thermodynamics. And that's a different thing than the first law of thermodynamics, but the second law of thermodynamics, and for Kelvin, makes for entropy, and it establishes this sort of time invariance in that there's at least two things that are regular. One is restitution and oscillation, the periodic, and the other is dissipation and attenuation, the evanescent. And so here, that perpetual motion exists or doesn't exist, it's not just perpetual motion, it's perpetual work. So something that's spinning, according to Newton, spins forever until disturbed by some principle of least action that it tips over, or whatever, the top that was mentioned. And the otherwise that he's just saying that physics is an open and closed system, it approaches and attains to these complementary duals, as a matter of factly, is of that there are these competing yet balanced concerns that provide these regularities, and regularities, or the rulio. So, and when there's an anisotropism, an isotropy meaning a sameness everywhere, and anisotropy meaning either a line through it or a detachment from the continuous or the discontinuous. Here, it's I'm not quite sure yet where he's going. Let's see. Same thing holds for the principle of inertia of Galileo. That these things make very good sense because, one, it reflects this ancient principle that what goes up must come down, because or it must fly, it must actively fly, or it must escape. It's called VE, escape velocity. Or it holds that what is in motion stays in motion, and this kind of thing. Einstein. In the same category, moreover, we find the fundamental hypotheses of the theory of relativity, which theory has led to an unexpected expansion and broadening of the field theory and to the superseding of the foundations of classical mechanics. It's an attachment to some of the aspects of it. Einstein has attached his theory of relativity to an attachment to a space local to each point in the space-time, the material point. Or otherwise, then, though, that he also says, and it has to be a continuum mechanics. Either way, Einstein needs a continuum mechanics if he's going to satisfy what he needs for a total field theory. The successes of the Maxwell-Lorentz theory have given great confidence in the validity of the electromagnetic equations for empty space attached with an electric field, and hence in particular to the statement that light travels in space with a certain constant speed c. In space, he's left in quotes. So space is what he's attached to his points in quotes, and in space is as of through otherwise the geodesy or relativities or whatever it so results in so motion. Here, whether it's the electrical field or whether it's vacuum, given that light propagates through no media at all, with a certain constant speed that's finite, yet large, c. Is this law of the invariability of light velocity in relation to any desired inertial system valid? If it were not, then one specific inertial system, or more accurately, one specific state of motion of a body of reference, would be distinguished from all others. In opposition to this idea, however, stand all the mechanical and electromagnetic optical facts of our experience. One specific inertial system. So it's kind of defined about the inertial system. And so if there's this consideration to approach the deconstructive account of the classical motion, and the inertia is so defined about the classical definition of force, which results acceleration, which results, according to velocity, inertia, and it changes to inertia or accelerations and caused by force, that when force is applied and acceleration results or deceleration, that those are also two different things with regards to the coming together or going apart of these inertial systems. That an inertial system going apart has no necessary tendency to return. That an inertial system coming together necessarily will pass or continue and go on together. These are ideas where what my theories about this include light speed rest frame theory, where light speed is really just constant going away from a central point, and that the frame itself is basically at light speed, and then light speed in every single direction otherwise is zero. And so that's the rest frame. It's not this privileged frame, it's its own inertial system, but any changes in effect to the acceleration and the change in inertia affect that. Then this rest exchange momentum theory is another one of my little theories. And rest exchange momentum theory would basically have that acceleration makes for travel of a space, the space of the body, because the body contains all its space, just like an atom is mostly space, as they say, kinetically. That it's possible to build up a restative in the exchange that carries forward and makes for why a herd is so pounding, or why stop and go is on the one hand so detached, and the other hand so clearly at a constant rate, that establishes a constant rate in otherwise discontinuous rates, and about how that is a fair and appropriate and easy way to attach these mechanics to relativity, and that is a pretty special thing and a simple little theory. If it were not, then one specific inertial system, or more accurately, one special state of motion of a body of reference, or its inertial systems, or its rest exchange momentum, in this light speed rest frame theory, would be distinguished from all others, or it would just exist. And then it would dissipate when it was not maintained. It would exist while it was restituted and oscillated and maintained, and dissipate and attenuate when it was not. Without violating this principle of least action, in fact, kind of accommodating it, because the frame is going somewhere. In opposition to this idea, however, stand all the mechanical and electromagnetic optical facts of our experience. Not necessarily. And you just have that they're so simply defined, and that when the clock spring results that after the ratchet latch mechanism it drives by a constant application of pressure, and as after a winding mechanism, the expenditure of the force meant to apply to that spring, that it is restitutive to its original form, the bar, as it is so bent that that just runs out, while at the same time simply maintaining. So it's to be read then that without such kinds of concerns is how we're reading Einstein, and it's so for him to say that it needs this kind of thing for this kind of explanation. For these reasons, it was necessary to raise to the degree of a principle the validity of the law of constancy of light velocity for all inertial systems. And it's not going anywhere. From this, it follows that the spatial coordinates x1, x2, x3, and the time x4 must be transformed according to the Lorentz transformation, which is characterized by invariance of the expression ds squared equals dx1 squared plus dx2 squared plus dx3 squared, that quantity altogether, or there's some of their squares, minus dx4 squared, or minus dt squared. And then in parentheses he has, if the unit of time is chosen in such a manner that the speed of light c equals 1. So he's talking about the normalized units, where when light speed is between 0 and 1, then anything greater than or at light speed is also equal to 1. This is not 0 and then 1, and then it's a bound. It's 0 and 1, and it's unbound. Because that's with regards to this Lorentz transformation. And the idea of the light speed rest frame theory is that just kind of follows it out the other way, because things are leaving the frame and taking the frame with them. And then for rest exchange momentum theory, it's kind of the same way. But here, though, it's also a new way in this book that he's rewritten. This is also the definition of a metric exists. Like in the path integral, as we've been talking about, this is the same writing for the space-time that the metric exists. And so anything that would affect the metrics would have to be a different kind of transformation. And then this is all attributed to Lorentz transformations, and then it's all reflected by the Laplacian, as earlier, is that the Laplacian for the Lorentz transformations is one way to go about it. There are others. And then if there's somebody to mention with regards to this, there's a fellow named Fitzgerald, and in the time of the big discussion about Lorentz and Lorentz invariance, because this is what Einstein attached to his description and arrived at for his theories, that he gained widespread acceptance, because after the Galilean is that this Lorentz invariance stands up after the Galilean invariance, so that it has for the Galilean and classical motion, the Lorentzian and classical motion with a fixed speed of light, some kind of limit. And so Einstein's framing of relativity in this framework as of what's today called having a metric, in terms of what is the gauge for the gauge theory, that Fitzgerald makes a case for real space contraction, space warp, makes a case that has what fits up with this light speed rest frame theory and with this rest exchange momentum theory. Fitzgerald is a special character, and Fitzgerald and Einstein together would make a relativity that would meet much of the desiderata and requirements of Einstein's total field theory that he's declared for the classical kinetic with respect to light as a substance, or that light is just the image of a substance. Light is always fleeting. Light is flux. Light is gone. Then is within the shadow of what moves. The light has a super classical model, and that is exhibited by things like the breaking radiation and Bremsstrahlung down from the electroweak and weak nuclear forces, and that light otherwise behaves in such a manner as that its propagation follows from its origin, whereas space and what carries with it carries that origin, and the images with it too. So, by this procedure, now back to Einstein, of course, and I hope it's clear where I'm speaking my opinion, and where I'm hopefully generously reading Einstein, and only insofar as it's a fair caricature his opinion. By this procedure, time lost its absolute character and was included with the spatial coordinates as of algebraically nearly similar character. The absolute character of time, and particularly of simultaneity, were destroyed, and the four-dimensional description became introduced as the only adequate one. In order to account all that, otherwise it would have been 3 dimensions and parameterized by time. In order to account also for the equivalence of all inertial systems with regard to all the phenomena of nature, it is necessary to postulate invariance of all systems of physical equations which express general laws with regards to the Lorentzian transformation. The elaboration of this requirement forms the content of the special theory of relativity. This theory is compatible with the equations of Maxwell, but it is incompatible with the basis of classical mechanics. Here I imagine he would introduce relativity of simultaneity, and these days it's really simple, and what people say is SR, special relativity, is local. It's local. In the statics, it's also in effect over time and over space, but in the dynamics, it's local. It is true that the equations of motion of the material point can be modified, and with them the expressions for momentum and kinetic energy of the material point in such a manner as to satisfy the theory, but the concept of the force of interaction, and with it the concept of potential energy of a system, lose their basis, because those concepts rest upon the idea of absolute instantaneousness. The field, as determined by differential equations, takes the place of the force. Now, these forces are a system of a field also. So these days when we say field theory, we mean all the fields. There's only one field for all the forces are in one force. It's a unified field theory. It's as few fundamental forces as possible, but after our deconstructionist and reconstructionist account, it's as many as necessary, but as few as possible. and then he's describing that it's what potential, what things fall to, not forces what things push at. Since the foregoing theory allows interaction only by fields, it requires a field theory of gravitation. Indeed, it is not difficult to formulate such a theory in which, as in Newton's theory, the gravitational fields can be reduced to a scalar, which is a solution of a PDE, partial differential equation. However, the experimental facts expressed in Newton's theory of gravitation lead in another direction, that of the general theory of relativity. Now, when Einstein says PDE, it's to be interpreted these days as including the nonlinear, because the PDE will not necessarily have, but its linear components captured in this breakdown, which reflect this Laplacian. So that gets back earlier in this discussion to the separation of the Laplacian and the Lagrangian, because what he really means, ultimately, is parameterized by time, t. And so when we read this here, there's a certain manner of generosity because the nonlinear analysis was not really established as a thing, and it might or might not have been available. That otherwise he's essentially reflecting that everything has to work out linear somehow also. Now that may still well be so, that the universe is linear and with respect to t. But it's a gauge theory, and thus any matters, and there's singularities, and so these would need to be solved by means of free analysis in the field and or basis of analytical freedom, birds of a feather, or something like that, that resulted that this generous reading was justified. Indeed, it is not difficult, Newton's. However, the experimental facts expressed in Newton's theory of gravitation lead in another direction, that of the general theory of relativity. See, here's where, yes, it's general relativity is first, and anything in terms of the space and the spaces and the spatial, it was in general relativity, it's about the kinetic, and then that establishes space concerns about space contraction. So I agree with that. Classical mechanics contains one point which is unsatisfactory, in that, in the fundamentals, the same mass constant is met twice over in two different roles, namely as inertial mass in the law of motion and as gravitational mass in the law of gravitation. As a result of this, the acceleration of a body in a pure gravitational field is independent of its material. Or in a coordinate system of uniform acceleration, accelerated in relation to an inertial system, the motions take place as they would in a homogeneous gravitational field in relation to a motionless system of coordinates. If one assumes that the equivalence of these two cases is complete, then one attains an adaptation of our theoretical thinking to the fact that the gravitational and inertial masses are identical. From this it follows that there is no longer any reason for favoring as a fundamental principle the inertial systems. And we must admit as equivalent in their own right also nonlinear transformations of the coordinates x1, x2, x3, x4. If we make such a transformation of a system of coordinates of the special theory of relativity, then the metric ds squared equals dx1 squared plus dx2 squared plus ds3 squared minus dt squared. I read dt for dx4 squared. Goes over to a general Riemannian metric of Bain. ds squared equals gu v dx sub p dx sub p. dx sub mu dx sub v, summed over mu and v. Where the gu mu v, or gu v, symmetrical in u and v are certain functions of x1 x4, which describe both the metric property and the gravitational field in relation to the new system of coordinates. Like we were talking about fields and classical fields and interfaces that are not fields, and then so this Riemannian metric is in a sort of Riemannian not a metric. It's, as it indicates, there's another origin which kind of has a metric and a place which has a metric. But it's sort of, this is about the usual definition of general relativity. These are the gravitational field equations, and it still reflects that ds squared is this vanishing in the small, and the utter increment, the utter individuation of analytical character, the sum of which over time or passage or area establishes finite value, but there are other ways. So he says this is a nonlinear transformation, and indeed it might be also special and singular, and that otherwise there are some other ways to look at, for example, rewriting terms in ds squared instead of rewriting terms in the metric. where the g of v, symmetrical and mu of v are certain functions of x1 dot dot x4, which describe both the metric property and the gravitational field in relation to the new system of coordinates. But going forward, of course, this is Einstein's theory of relativity, and it's general relativity in its usual stated form as after his study of it all his career, and so thusly it's to be read that Einstein's talking about his theory, and it's fine. It's not necessarily without its issues with the classical. Here he's just describing how after gravitational mass and inertial mass end up looking the same, that where they're not so much about these inertial systems, that he's making a place for it like so. The foregoing improvement in the interpretation of the mechanical basis must, however, be paid for, in that, as becomes evident on closer scrutiny, the new coordinates could no longer be interpreted as results of measurements by rigid bodies and clocks, as they could in the original system, an inertial system with a vanishing gravitational field. An inertial system with a vanishing gravitational field. See, this gets into the contraction and dilation, and the idea is it's space contraction, and it's to work up as a constant of some properties of acceleration that make it so that it basically turns that in a body and the application of the forces, how it's so then that for rigid bodies and their contents of the spaces around them, that there's these sorts of transforms which still satisfy for these invariances, these things, that it is so that when otherwise in extremis or at the nonlinear, the field otherwise vanishes either way, an inertial system with vanishing gravitational field, that it's almost as like a gravitational field with a vanishing inertial system when acceleration is no longer applied to it between two bodies. Passage to the general theory of relativity is realized by the assumption that such a representation of the field properties of space already mentioned by functions GUV, that is to say by a Riemann metric, is also justified in the general, emphasis the author's case, in which there is no system of coordinates in relation to which the metric takes a simple quasi-Euclidean form of this special theory of relativity. So that points back to the quasi-Euclidean, his discussion of the space and why his special relativity has local space. The quasi-Euclidean, but that otherwise there's this notion of Fitzgerald and in the warp, and that still results in Euclidean because it's a transfer of content besides just the space that it did and will inhabit for what it does. What it did and will. Now the coordinates by themselves no longer express metric relations, but only the neighborliness of the things described, whose coordinates differ but little from one another. See, this is where the idea is to keep the coordinates and have for their metric relations, but only the neighborliness of the things described. This is still establishing that it's a continuum of things. This makes it so that whatever nonlinearities still work out, that there's a usual continuous smooth function that defines things so between them, compared to like starts and stops, or the humps of the Loch Ness Monster, or whatever it is. All transformations of the coordinates have to be admitted so long as these transformations are free from singularities. This is the idea of basically that any impulse is a singularity. So these complementary duals work up that really in a field of all potentials that somehow this is all the fall in. Again, while I'm reading this for Einstein's opinion, I'm reading it for my opinion. So just to make that clear. Only such equations as are covariant, which gets into why they're coordinate free. Coordinates are built in, they're left out. In relation to arbitrary transforms in a sense, have meaning as expressions of general laws of nature, postulate of general covariancy. Again, keeping in mind that the laws of nature are in the theory, and they're not to imply that it's unnatural, otherwise that they don't have a physical interpretation. It's just that it's natural where they do. And that that clearly you don't have a better law of nature until it has a better physical interpretation. To nature. Okay. The first aim of the general theory of relativity was a preliminary statement which, by giving up the requirement of constituting a closed thing in itself, could be connected in as simple a manner as possible with the facts directly observed. And this is where it's difficult to have an inertial system with respect to another inertial system which work on each other and accelerate each other. But if you just have things everywhere in their own little inertial systems with respect to gravity, at least has that gravity is kind of this overriding thing in space-time, even though it's all matters of orbits. And this fall gravity, for example, as a field for a field theory, but here it was for bodies ready to be computed in a piece. Newton's gravitational theory gave an example by restricting itself to the pure mechanics of gravitation. This preliminary statement may be characterized as follows. 1. The concept of the material point and of its mass is retained. A law of motion is given for it. This law of motion being the translation of the law of inertia into the language of the general theory of relativity. This law is a system of total differential equations, a system characteristic of the geodetic line. This is, there's a geodesy in general relativity, and objects move on it. But it's kind of the same as the Newtonian because the geodesy is always consistently reevaluated, and it's according to, it always points to the source, not the image. And that here it's defined by a system of total differential equations, that it's just a Lagrangian for everybody, and otherwise it's this continuum mechanics that's being talked about, that there's a hypothesis that the universal field is continuous. Because if it was not, then there would be a place where nature was lawless. And if so, it would be everywhere, which would result in the same system. That there isn't anisotropy at all is just the field of gravity. Well, that's my interpretation, but it makes for a very simple principle of least action and principle of least reasons why things occur. Item 2, preliminary relativity. In place of Newton's law of interaction by gravitation, inverse square mass, we shall find the system of the simplest, generally covariant differential equations which can be set up for the GUV tensor. It is formed by equating to 0 the once contracted Riemannian curvature tensor. R sub UV equals 0. This is a usual kind of principle of least action, and that things according to then this is computing the geodesy. And at any given moment, you can say, okay, I've computed the geodesy, and every material point's placed in it, and I've determined their velocity. And at the next time step, however small that is, it will go straight in that direction. And then the entire thing is recomputed at once. Every time step. Einstein continues, this formulation permits the treatment of the problem of the planets. More accurately speaking, it allows the treatment of the problem of motion of material points of practically negligible mass in the gravitational field produced by a material point which itself is supposed to have no motion. Central symmetry. It does not, so central symmetry here he has as that principle of least action, and that there's some other kind of symmetry would be like, what is reflected, or like the symmetry of classical and potential and that kind of stuff. Central symmetry. It does not take into account the reaction of the moved material points on the gravitational field, nor does it consider how the central mass produces this gravitational field. As above, it's computed, the geodesy is computed here by a fall of gravity that is superclassical. Analogy with classical mechanics shows that the following is a way to complete the theory. One sets up as field equation R ik minus 1/2 little g I k r equals negative t sub ik, where r represents a scalar of Riemannian curvature. Curvature is an underdefined concept. T sub ik, the energy tensor of the matter in a phenomenological representation, mass energy equivalence. The left side of the equation is chosen in such a manner that its divergence disappears identically. It's contrived. The resulting disappearance of the diversion to the right side produces the equations of motion of matter in the form of partial differential equations for the case where T sub ik introduces, for the description of the matter, only 4 further functions independent of each other. For instance, density, pressure, and velocity components, where there is between the latter an identity, and between pressure and density an equation of condition. So here he's kind of just described that there's this cool things in terms of like the oscillative and restitutive, and the dissipative and attenuative. You know, for example, that which is going keeps going, and that which is gone gets gone, or this kind of thing. In terms of this symmetry condition and the balance and the central symmetry, establishes for the principle of least action really much as after description that his equations are then whatever's Lagrangian, this is so. And what it still provides is a separation from the Newtonian mechanics to makes it for that this space contraction can still be a thing because it's in the space, and it's spatial. And it helps explain for a way to get up above about Einstein's attack on Newton. For the classical and mechanical, that relativity is the way for this, as he mentioned, and that then it's to be let out though about that for the nonlinear and the singular, that it has to be linear and singular and non-singular again, or that it has to be, you know, circular and singular in a sense. Now that's getting a little bit loose there, but only to the extent that this view of the complementary duals makes for his equation here is basically just the setup of this kind of complementary dual, and the idea is that then whatever he's so contrived is like these systems describe systems of equations of motion. Sure they do. Sure they do. They're not given, but they're described. It's not established exactly that they exist or in what conditions they exist, but it's exactly they exist. It's not established so much that the field equation is uncontrived, but it's set up that its divergence disappears identically, that it's standard. That what is standard and real valued and thus a solution in this system is like so. By this formulation, one reduces the whole mechanics of gravitation to the solution of a single system of covariant partial differential equations. The theory avoids all internal discrepancies which we have charged against the basis of classical mechanics. There are more. It is sufficient as far as we know for the representation of the observed facts of celestial mechanics. But it is similar to a building, one wing of which is made of fine marble, left part of the equation, but the other wing of which is built of low-grade wood, right side of equation. The phenomenological representation of matter is, in fact, only a crude substitute for representation which would correspond to all known properties of matter. Then he goes on to describe it's a lot easier than on what results from Maxwell's fields, but here I'm going to leave it at that for the moment, because there is, though, that what he's left is the place for gravitation, and then for the uniting the fields is the idea is that the strong nuclear force is the same thing as gravity, because it's a fall gravity, and so the asymptotic freedom, which results from the strong nuclear force, just makes it so that then the charged particles and the electrons around them make for an atomic and nuclear model with subatomic particles as with charge, and that these charged particles are the force carriers for electrical force, and that the atom is the force carrier for the kinetic force, that the centrality of these things makes up for so why they have all these principles of least action in effect, that at the same time something like a magnetic wave is a resonance, which is of low or high energy or force, how strong it is, and compared to how weak it is, maybe in terms of otherwise everything is kept apart. Everything's kept apart by the static charge. You know, thinking about ways to make it so that what's the usual simplest principle, it has some kind of opposite effect. Then in our classical milieu, its real mechanism, it makes it so that that's how it adds up. So in this sense, one could look at that a way to make things that look like really strong effects, like the magnetic effects, correspondingly weak again, and that things like the charge is just so strong in this tendency of something to disappear everywhere for a current to connect or something like that. These are the kinds of things, and again, in the notions of complementary duals, which help to advise how and why, especially why, in the question words, how and why, and under what are the conditions there can be this kind of deconstructionist, reconstructionist account that results in A, all the science that backs Einstein is still not dead. B, all the science that backs Newton and Galileo, ... C, all the science that addresses the modern experimental setup yet lives. Or as they say, supersymmetry is not dead again. And then in terms of the Lagrangians in this, then we also need new mathematics for these superclassical forces in this superclassical theory of potentials and the theory of omega potentials and theory of some potentials ends up being in terms of those then simply, and without the notion of the perpetuum mobile, or that otherwise things are just as natural as possible. Again, as Einstein began this section, available to the object sense via induction, then descriptive to models, which so modeled by simple models that can be so replicated that it can be shown that things work this way all throughout the universe. All right then, hey, have a great day. I hope it is enjoyable, and so long.